Okay, so today we're doing another prac. I'll have to do a bit of a lead into it as well. We're doing evidence of the Bohr model. So you remember the Bohr model of the atom is the one where we have the nucleus and we have the electrons in shells going outwards. Now, our syllabus outcome for today investigate the energy levels in atoms and ions through collecting primary data from a flame test using different ionic solutions of metals and examining spectral evidence for the Bohr model. It also says, and introducing the Schrodinger model, but we're not going to do that today. We're going to do that another time. So the stuff for today. Firstly, some revision questions there at the start of page 33. Have a go at them. Um, if you've done them, we'll go through the answers now. So electrons exist in shells within atoms. Now, the outermost shell is called a valence shell, and the valence shell determines the charge the atom will get when it ionizes. So it will determine whether it goes to plus or minus and how many are lost and gained, whatever. Atoms with 1, 2, or 3 valence electrons prefer to lose them, whereas atoms with 5, 6, or 7 prefer to gain them. And those with 4 can either gain or lose electrons. So let's have a look at a bit of the evidence for the Bohr model of the atom. Now, the major piece of evidence that helped confirm the Bohr model of the atom was the discovery of spectral emission lines. Basically, when an element is heated enough, it emits lines at very specific wavelengths. Okay, so you might remember wavelengths from year 10, so the distance from the crest to crest of a wave. With light, they're in the ranges of hundreds of nanometers, so by 10 to the minus 9 meters. Now, with our spectral lines, when an atom's heated up enough, we get these very specific emissions at certain wavelengths. Okay, not all of them are super strong. Some are stronger than others, but they're each of them are specific to the element that's being heated. Okay, so if we have a look at these, helium has a lot at the shorter end of the spectrum. Oxygen has a lot in the red orange sort of section. Neon's kind of spread out. So is argon. Xenon, there's not much between that 4 to 500 sort of area. And so what we can do with these is we can actually identify atoms based on their spectral lines. So at the top we've got an unknown. Now because this is like a fingerprint for the atom, we just try to find which one matches. So obviously helium and oxygen don't because they've got lines where there's none in the unknown. But if we look at neon, it kind of perfectly matches up. So we have this line which matches with that one. That's that one. That's that one. So we can see that there's got the same lines at the same point. So the unknown gas in this case is neon. Okay, so it's the same for every element's different. Now, why is that? So the light comes from an atom absorbing so much energy that one electron jumps from a lower shell to a higher shell. Okay, so we had our 1n, 2n, 3n shells. If we had one in the 1n shell, it can jump up to the 2n shell. Now we call this being in an excited state. So just heat alone can get that electron into an excited state. And the normal state we call a ground state. So here we've got the ground state of helium. Okay, 2 electrons in the 1n shell. Give it enough energy, then one of the electrons jumps up to the 2n shell, and that's what we call our excited state. Now, each jump has an associated change in energy. Okay, so basically, the more energy we put in, the more it jumps. Now, when the electron drops back down into its ground state, it emits that energy as a photon. So we're taking heat energy, it's absorbing that and getting into an excited state, and then it emits that as a photon, so as light energy. Now, as the wavelength of the photon is dependent, the wavelength of the photon is dependent on the energy of the photon. Each different energy jump will produce a different wavelength of light. Okay. Now, electrons in an excited state. Um, this is just an example of it. So in this case, we had an electron jumped up to n equals 2. It then dropped back down and it emitted that photon. Now, for those in physics, the formula is E equals hf, so it's actually dependent on frequency rather than wavelength. But for light, it's there. We can say it's also dependent on wavelength. But anyway, I'm getting off track. So yeah, that's how we get that photon being emitted. Um, Now, electrons in an excited state, they may be more than a single shell higher, giving rise to multiple spectral lines. So, um, we saw back at those spectral lines that there was lots of different types. Now, they can come from an electron getting excited up from the ground state. So let's say, look at helium again. We can go from the 1n shell up to the 4n shell, and there's all different types of drops that it can do. So it can just drop this first one straight back to n equals 1, which emits one type of light, or it can go down to 3 and then down to 1, or down to 2, then down to 1, or it could just drop one at a time, that sort of thing. There's all these different possibilities for it dropping back. It doesn't have to drop all at once, it can drop several different times. And so what we're going to be doing today is we're going to be observing that in the lab. Okay, now it's something that you would have done before, probably several times. It's a really good prac. It's the flame test. So where we get the Bunsen burner, spray some solution in, and we get the flame. Now, normally you would probably just have looked at the color. Today we're going to be looking at the spectral lines through a spectroscope. So there's a little black box that splits the lines up and puts it against a scale. Okay, so whatever wavelength of light is being emitted, we can actually see that against a scale. Now, there's a picture in your workbook on page 35 on how to use them, but I'll show you how to use them. But we're going to be doing that instead of just observing the color. Okay, and so that's it. So we'll do the prac and go from there. So that's all for today. Oh, sorry, I forgot to mention. I'll also show you some discharge tubes. Now, it's a similar process, but instead of spraying something into flame, we're just going to use some high voltage electricity, kind of like neon lights. So we're going to get some emissions of different elements and have a look at them. Now, we're not going to look at them through the spectroscope because sometimes they can produce X-rays, so we're just going to kind of observe them very quickly um, and not linger on it and not look directly at the light too much. Okay. So yeah, so that's it for today.